Hello, calculus fans. Going to continue our discussion of melting snowballs. In this one, I'll do the actual solving, talk a little bit about the calculus. If you missed the previous videos, I have some visuals I made. It's a nice face I'm making there. But I wanted to explain how I made this visual with this melting snowball and the fact that you can see. This is just the time going forward. You can see that it appears the radius or diameter, however you want to think about it, is decreasing at a constant rate. That's definitely what's happening in my visual in the corner. Okay, so I do want to remind you, I'm Dr. Andy Lovelace. I have all these resources if you need help. I'm making this channel just to have a little fun with this and hopefully help more people. But if you search my 207 materials, the stuff I'm about to do applies to Math 124. When you do related rates, you often see problems like this. 125, we start to solve things like this. 207, we study them in more completeness. And then the visual I make actually uses spherical coordinates, which is 224. So I'm trying to do these topics that I see overlaps with a lot of our courses, and this is one of them. Okay, so the main assumption, and my goal here is to kind of talk about some of these ideas. So the main piece is that we have this thing, some assumption we pull from science. So I want you to think about this as part of the scientific method. We make an assumption, we use the math to test it out and experiments, and if it fits, then we've learned a great deal of information and we can try to predict how things are going to happen the next time we encounter it. So a lot of differential equations is about predicting the future, and we're willing to spend a lot of time, and honestly, this is not a lot of time, but we're willing to spend a lot of time to see a little bit into the future. Okay, so I think people start to think, oh, this is hard, but if it takes you 10 minutes and it predicts what's going to happen in the future, for any situation, it seems to me like it might be worth it. Okay, so the assumption is snow melts at a rate proportional to its surface area. If there's more surface area, it melts faster. If you crush the ice, it melts faster. So people have observed this, and we just observed this happening. And I'll explain why in a second. So in order to sort of put this into an equation form, so I think of this, or not just me, but we think of this as the dynamics. The way in which the governing principles in which things are moving. Even when you're throwing things around a room, the dynamics is, I'm assuming there's gravity. That's the governing dynamics. Now, how you enter that is what we call your initial conditions. And so in my situation, my initial conditions, where I entered this dynamic world, were this. My initial radius was, in this example, was about 2.5 inches. In my ending radius, pretty much things melted away at about 2.25 hours. So about 9:15 is when it actually completely melted, and that's when this was 0 inches. So both of these things play an important role. You can see that if you start throwing a ball around the room, you say, well, how can it be the same dynamics everywhere? Well, you're changing the initial conditions depending on where you initially throw it from, what your initial velocity is, but the dynamics are the same. Okay, so here we're going to assume the dynamics are this. So a few things I need. The surface area. So first, all three of these things are changing. That's where the related rates comes into play. T is our variable, and we have these other variables that all depend on it. So anytime I take a derivative, I'm going to need to take a derivative of any of those things appearing. So anyways, the surface area of a sphere is pi r squared. And I could talk about that a lot. There's an interesting property about the volume of a sphere and the surface area being the derivative with respect to r. I can talk about why that is, but that's maybe for another video. Okay, so that's what we get. The problem is there's all of these pieces. So one way to do this problem, which is not the best, but illustrates a few other things. Sometimes it's good to do things not the best way, just so you have more examples of how to do it. So if you want to get rid of the r and make it a v, you have to solve this. That leads to kind of a mess. Okay, and I have some work prepared over here, as you can already see. So if I solve this for r, there's a little algebra challenge for you. You're going to have 3 over 4 pi when you divide. You're going to have v. You're going to take the cube root of all that. And if I was doing that, I would separate the variable. Okay, that we're going to shove in. And I'm not going to do every detail, I just want to give a little bit of this into here. That's usually the sticking point for students. Again, this is not the best way to do this. But then all of this will be to the 2/3, and then there's all sorts of mess here. Okay? So if I was doing this at this moment, I would say, well, all of this stuff, this constant, I'm going to get a v to the 2/3, and then I'm going to get this big mess. And the mess I'm just going to call a for the rest of the problem. So it's going to be 4 pi. I'm just collecting all the constants. And there's going to be a 3 to the 2/3. It's 2 because I'm squaring all this. Over 4 to the 2/3. And I find that when things like this come up in class, we could spend like 5 hours talking about this. Students and how we simplify and how we deal with roots. And that does simplify because 4 over 4 to the 2/3 is 4 to the 1/3. Pi over pi to the 2/3 is pi to the 1/3. The thing to recognize is if you have an expression with lots of radicals or roots, there's probably a way it simplifies. But that's not what I wanted to talk about here, so let's not get too distracted. So we have a constant there. Okay, so let's keep that handy. I'm going to move this over. I'm playing around with my Lute technology, so there's our constant. The other comment I want to make is when you're setting up differential equations, now is when you can use those related rate skills. You say, well, if this is true about the derivative of v, what if I differentiate both sides with respect to t? And that's where you need to think in terms of related rates. R and v and s are all changing. And that's where the chain rule is very valuable. So the derivative on the left is 1 times dv dt. And the derivative over here is 4 pi r squared times dr dt. That related rate stuff is actually really valuable if you're studying any sort of dynamics or how things are changing. And in this case, it comes out really nice because we're making the assumption that the change in v, now, I know this is pretty math heavy, but just bear with me for a second. What's cool is that you can then cancel these and you find out that this assumption leads to dr dt, or the radius, changing at a constant rate. So this is what we do. We analyze it, we solve it, we think about it from a few points of view. The more you do that, the more understanding you have. And if it fits your model, it's worthwhile, especially if you're going to study melting things. Okay. So that's a little bit of the kind of case for what's going on. So that leads to these two differential equations. One that's the differential equation for v, one that's the differential equation for r. We probably could get the differential equation for s too, but actually I've never done that, but that's maybe for another day. Okay, so let's get rid of all this. Now we're set. At this moment, you could hand this problem to anybody in a differential equations or Calculus 1 or Calculus 2 course, and they hopefully would know how to do it. And what I mean by that is, this is a separable differential equation right here. We can get the v to the other side, and so we get v to the negative 2/3 dv. There's a discussion to be had there about what that means, but take those courses, integrate both sides, and this gives you v to the 1/3. This gives you a 3. This gives you negative k times at plus a constant. I call this c sub 0. And then solve. Divide everything by 3, which is what I did here, and then cube both sides. And then I called this c. So there is the formula for the changing volume. You do have to remember there's this messy constant a in the middle. If I wanted to make this formula nicer, I might simplify this, I might factor it out. But the next step would be to put in initial conditions. Now in this case, my initial conditions I gave were in terms of r, so you'd have to plug in and find the corresponding v. That would not be bad. But let's solve it the other way and see what happens. So again, if you wanted the initial conditions for v, you would say v of 0 is 4/3 pi r cubed, and r would be 2.5 cubed. And v of 9, 0.25, would be 4/3, would just be 0. What am I doing? I was going to write 4/3 pi 0 cubed, which would have been fine. Okay, so there you go. You can find those constants. Part of the reason I wrote it this way and didn't simplify is I wanted the k's to mean the same thing. The c's don't represent exactly the same thing. I encourage you to sort of go through and find what they are. And it's because of the organizational way I've written it. But this is much easier to solve. This is just a constant. This is the general, if these dynamics are right, this is the general solution. So if you assume, so we learn other things as well along the way. If you assume that snow melts at a rate proportional to its surface area, you get this. This one's easy to plug in for. So now let's use our information and do this. When you plug in 0, you get 2.5. That means this has to be 2.5. When you plug in 9.25, you get 0. So we're going to get 0 is r, right there, when t is 9.25. 9.25. And all of this is, approximate. So if I solve for k is going to be 2.5 divided by 9.25. And I've got my trusty little calculator here, so let's do this. I got approximately, this is approximately, 0.27. So when we say things like it's proportional to here, I think of this as a percentage. Like if you go into a bank account and they say you're going to get 27% a year. Now in this case, it's 27% an hour. In these situations, we say it's compounded continuously. You can go into a bank and talk about what that means. But it's some percentage of the surface area to give you the rate. So there's how precisely to interpret that in terms of units and the situation, that we'd have to talk about that a little more. But just to give you a casual way to think about K, it's like a percentage. We're losing like 27%. And in this case, I was in hours, about 27% an hour. Okay. Then we got it. The radius is, I think I'd want to put the 2.5 first. 2.5 minus 0.27t. And that's how I made my visuals, is I knew that. And then if I wanted the volume, rather than write it this way and co-insult that c, I would just use the fact that 4/3 pi and then r. This is a really accurate model for a melting snowball. We've effectively looked into the future here. Now, a couple things I'll show. So this, just briefly, there's the melting snowball. I think I shifted it up so it looked exactly the same in my previous visuals. But all I did was this. I entered this function. And you could change this. In fact, maybe I'll share this. Let's copy this. Here we go. Now you can do it yourself. You can melt any snowball. I'll put it in my description when I am here at the end. Make it a little bigger. So I'll put that in the description when I make this video, but then you can play around with that all you want. It's just a free online 3D calculator. And you could change these numbers. You could say, this is my initial radius. This is my K. Now the K is interesting. There's an opportunity here for a project if somebody wanted to do it. I just computed the K using a snowball with radius 2.5, computing it in hours, and using a room that was about 70 degrees. I wasn't precise about that. It would be interesting to see how K changes as you change the room temperature. Like what if it's outside at 40 degrees? And then you can make a little table that says at 70 degrees my K was this. At 60 degrees my K was this. At 50 degrees, that's what people do. Researchers do these things and make a collection. If you go like on the NASA website, as a collection of these experimental data that you can use as your air resistance formula. So this could be value if you were doing something that was studying lots of, and it would take several days of experiments. But then you'd have a list of what's the correct K to use, and then if someone else came along, they could study melting. So that's a little bit of going further. But all I did is I plugged this in. Now this is spherical coordinates, which is a nice way to make a sphere. There's other ways to do it, but it tends, if this becomes an issue of how do we make it look nice. So anyways, I did a parametric surface. There's other things going on. But all I did was plop in the radius, and then I have this little mover. There you go. Now, in order to make it match up with time, I had to slow it down, because this is not actually time. I had to slow it down to sort of match. But the point I was showing was not... The point I was trying to show is that it was at a constant rate. There you go. That's it. So this is all, as I said, part of this scientific method, and I think this does a good job of showing you a few things. This also has some interesting behavior in terms of theory, and so that's what I'll do in my next video. But I hope you find that interesting, and I hope someone takes me up on this project. This could be a project for one of your classes, and say, okay, if it's 70 degrees, what's K? So I'm proposing that K is 0.27. I think that doesn't depend on the radius of the snowball. It might depend on the type of snow. Like I did this after the snow had been on the ground for several days, and I wonder if it's like more tightly packed. I'm sure that affects it. And so then you could have another table about that. But then you could say, what if it's 60 degrees? What if it's 40? And then you could start to predict how long is the snow going to stay on the ground outside. So you can see how things naturally lead to more questions. Just have to ask why, have a little bit of math. Okay, hope that's interesting. I'll stop there.